Yeah, good morning, everybody. Thank you for inviting me to share a few thoughts on some logistics aspects of the smart city. First and foremost, I would like to recognize the work of my colleague, Mr. Lakshika Dilshan Vialat, who contributed to this work. Now, I picked two of the common definitions of the smart city. And one defines the smart city as one that has digital technology embedded across all city functions. From Dubrovnik, we actually heard some of the examples for that. There's another definition from Mr. Singh from Frost & Sullivan: smart governance, smart energy, smart building, smart mobility, smart infrastructure, smart technology, and a few other smart things. I would like to focus on two of these smartnesses, and that's the embedded digital technology and smart infrastructure. If you have classical appliances and you merge them with the Internet of Things, you get very interesting things. In the private sector, this is known as, under the buzzword of Industry 4.0. But there are also some smart city applications which may make a city even smarter and contribute also to the city management. Because it enables you to put a budget-priced, affordable sensor behind every single spare part, wear and tear part, filter, everything that needs to be exchanged from time to time, and to monitor the progress of deterioration of this spare part. And this enables quite interesting logistics concepts. So I would like to segment my presentation into three parts: description of the issue, smart logistics as a contribution to the issue or to solving the issue, and the consequences of this. Now, what is the issue? Cities require infrastructure, which in turn require logistics support, which in turn binds capital and requires storage capacity. We know from economics that capital bound is always a bad thing. Storage capacity is even worse. So let's try to minimize that. So can we use Industry 4.0 concepts to optimize on that? Well, if we are able to put a sensor behind every wear and tear part, we can monitor its state of deterioration. So we can define a warning level, here depicted in yellow, orange, something like that, which gives us a warning signal. Look, the part is still running, it's still usable, but you've just got 400 hours left on average with a certain standard deviation. It's about time to reorder. And then, of course, at some stage, the deterioration becomes that bad that the part fails with a probability of 1. That would be the red line. Of course, the warning level can be shifted. You will have a tendency towards lower warning levels for mission-critical parts. You will have lower warning levels for parts with a very long replenishment lead time or a very high variance in the replenishment lead time. Or, in the opposite case, you may also shift the warning level up. Now, we conducted simulation runs on the effect of condition-based maintenance. Condition-based maintenance meaning you monitor the state of deterioration and then trigger some logistics processes, reordering particularly, and the maintenance, scheduling the maintenance operations in response to this warning level. Now, we used a completely unrealistic benchmark. That is the immediate in situ availability of all parts, completely unrealistic. You never have that. But that's our benchmark. Something fails, you have it on shelf, readily available. That's the wonderful benchmark. We conducted simulation models with different scenarios using any logic, implementing a finite state machine, simulating the deterioration of those parts. The average lifetime of a part was 1 year. We simulated it over 5 years, and we conducted thousands and thousands of runs. There are stochastic logistics processes. Also, the deterioration is a stochastic process. We assumed very, well, parameters that are not very nice, let's put it that way. 40 days replenishment lead time, 10 days standard deviation is not very nice. That's a pretty cumbersome logistics process. It should usually, at least within Europe, be organized a bit better. But we intentionally chose a very cumbersome environment. Also, the failure increase, or the failure probability increasing with the duration of usage was set in a very unfavorable way. The deterioration under 10% indicates a very small probability of failure, 0.5%, 5 per mil. Whereas beyond 90%, you've got a probability of failure in each period of 1/3, which means you have a very steeply increasing failure probability. So when you get the warning level, you have an exponentially increasing failure probability. The target value, or target variable, was minimized downtime, and the control variable was shifting the warning level. Result: condition-based maintenance almost reaches the benchmark. And we are talking about a scenario where in the benchmark, everything is always available on tap. If we set, for instance, the warning level at 80%, the detailed results are available, including also the simulation in AnyLogic. But if you set, for instance, the warning level at 80%, you get a 93% availability, and we're talking about 0 stock. No stock, nothing. No capital bound, nothing. And yet you get 93% availability in a scenario, as I would like to reiterate, whose basic parameters were not set that favorably. What are the consequences of this technology? Well, the main question is, and this is where e-government comes in, what happens if you get the trigger signal, reorder? What happens then? Do you have a logistics process that can pick up on the signal and trigger the appropriate reordering, replenishment process, the connection to the budgeting system, ideally to payment? Basically what would be known as an order-to-payment system. So in the industry, such systems are in place. Are such systems in place also in the smart city? So the smart city in some aspects also requires, and we should not forget that, back office applications that help you handle the back office processes triggered by the smartness of the front office. Also, everything that reduces variance in your processes is appreciated. It's not so much the overall duration. It's better to have a 50-day replenishment lead time with 1-day standard deviation rather than a 10-day replenishment lead time with 20 days or 15 days of variance or of standard deviation. So everything that reduces variance, everything that increases predictability is appreciated here. Of course, public procurement should also be in place, and it needs to be linked with asset management and the maintenance services themselves, because it's not only to have the spare part available, but to send the people, first and foremost, to identify the spare part when it's available, where it should go, and then to have the maintenance crew ready to go out there to the piece of equipment that's somewhere in the city and change the stuff. So the smartification of the infrastructure is enabled by that, but it requires the appropriate back office processes. And that, of course, also requires further research needed for this interaction, because what Industry 4.0 can contribute to the smart city is the signal. What you do with the signal, that is classical back office e-government. Thank you for your attention. And think we are now for the questions.